To get maximum value from the many functionalities of the Student VectorCalculus package, the user must first understand its underlying structures and the relationships between them. So this webinar is designed to answer the question, what does a user need to know about this package to implement it efficiently and effectively? So we need a starting point here. And let's take as our starting point some investigations that you might do if you jumped into this package and started poking around. You might find this vector command, and with it you create a vector, and when you hit the enter key, this is what you're going to see. If you think about it for a bit, you might conclude that this symbol e sub x and this one e sub y stand for the unit basis vectors I and j. So you want to test that out, so you try something like making a polar vector. So you type this, and you get back e sub r and e sub theta, and you begin to wonder, what are e sub r and e sub theta? Because you have this vision in your head of polar basis vectors being point dependent. So you try something else. You try to create what is clearly a Cartesian vector mapped to polar coordinates, because that's what this map to basis command does. Well, you get back the same e sub r and e sub theta, but now the components are treated as Cartesian, and you get the square root of x squared plus y. So that's r, and this is theta. I don't think we're clearing up any mysteries yet. So you try poking around with this thing called a vector field. And now the vector field comes back with e sub x, but it has a bar on it. And e sub y has a bar on it. So this does not have a bar. This has a bar. Let's try making a vector field in polar coordinates. Well, you get an e sub r bar and e sub theta with a bar. Things aren't getting any clearer. Let's try this. Let's take a vector field that's clearly Cartesian, xy, and send it over to its polar representation. Now you get just e sub r bar and r in front of it. What happened there? Well, if you think really, really carefully, you realize this is a radial field. The xy is actually a radial field. And so over in polar coordinates, you have a radial field. That means Maple must know something about these letters x and y. So let's use u and v where Maple doesn't know anything about those letters. Do the same thing. Vector field. Maple will treat that as Cartesian. Send it over to polar coordinates. And now you get an expression here and here that will only reduce to r if you set u equal to r cosine theta, because that will give you a cosine r cosine squared. You put v is r sine theta, you'll get r sine squared. You factor out the r, cosine squared plus sine squared is 1. That r is this r. And if you look here and you put r cos theta, you'll have a cos and a sine. And here you're going to get a sine and a cos, minus and a plus, and that's why that term drops out. So what are the structures? What is Maple really doing here? Now, one thing that we can do for sure is not to use Maple and to do the calculation of changing a vector to polar coordinates. Okay, so this is the position vector. This is all just typed out. This is not computing with Maple. R cos theta, R sine theta. If you differentiate with respect to r, you get a unit vector, which is the unit vector e sub r. I'll put a hat for unit, pretty typical notation. That's the moving basis vector. If you differentiate with respect to theta, you get this vector. You normalize, so you can divide out that r, and this is the unit vector in the theta direction. This is what you recognize and you find in textbooks. Now, if you write out what this vector is with respect to the I and j basis vectors, and this one with respect to I and j basis vectors, you can solve for I and j in terms of these vectors e sub r and e sub theta. If you then take those expressions for I and j and put them into this Cartesian vector ui plus vj, you will get this mess, in which you can collect terms. You get er, e theta, and if you go back over here, you'll find out that's exactly what Maple gave you. So this expression that Maple came up with when it took a Cartesian vector field and mapped it to polar coordinates, this is the correct expression. Maple does this correctly. That is what you're supposed to get. And the explanation here about the x and y as opposed to u and v must mean that Maple knows something about the letters x and y that you did not expect. A fundamental insight into what's happening here in this package is the identification of point and position vector, which we are familiar with in Cartesian coordinates. When you do a multivariate calculus course and you have that first unit on points, lines, vectors, planes, you make that identification in Cartesian coordinates. But in this package, that identification of a point with a position vector is carried over to non-Cartesian coordinates. But to do that, you have to invent a fictitious position vector in non-Cartesian coordinates. Think about points and coordinates a bit. At top level, points are generally lists, but they don't carry a coordinate system. They're just a list. In the vector calculus package, because points are going to be represented by this fictitious position vector, they will be able to carry a coordinate system. So you give a little and you get a little. Well, that paradigm has implications. And let's use this example to amplify what those implications are. Okay, this is a little patch of the Cartesian plane, xy, and I have superimposed the polar coordinate curves, circles, concentric circles, and radial lines. And this vector er and e theta are the unit vectors along those coordinate curves. Now, these formulas are familiar. R is x squared plus y squared square root, and arctan y over x for theta. If you have the coordinates in Cartesian terms, you have an x and a y, you can compute an r and a theta. And that r and a theta can be placed in this rectangular version of a polar plane. And in this polar plane, vectors er and e theta, no decorations on them, are invented to allow this point to be represented as this vector. This is the r component along this direction, and this is the theta direction along this direction. Of course, you have the inverse map. But over here, what you might be familiar with as a vector with a hat on it. Maple puts the bar on it. So remember, we saw those basis vectors with a bar on them. Those are the vectors here. These unbarred vectors live here, and that's the fiction that's created in order to have this notion of a position vector representing a point. So now let's talk about the coordinates that this package can handle. It recognizes these 5 coordinate systems: Cartesian in 2 or 3 dimensions, polar, cylindrical, spherical. Note that for the purposes of this package, Cartesian is spelled with a lowercase c. There are default coordinate variable names recognized: xy and xyz, r theta z for cylindrical, and r phi theta for spherical. So by limiting the coordinate systems down to 5, which is what you would normally use, let's say, in a first course in vector calculus, Maple compensates by recognizing a default set of coordinate names. If you are in the vector calculus package, not the student version, but the vector calculus package, you can access all of the orthonormal systems that Maple recognizes, 30 some odd systems, whatever. But there are no default variable names, and consequently you must constantly define coordinate systems and coordinate variables every time you turn around in that package. That's my preference for the student vector calculus package. It's more forgiving, a little bit simpler. Also, there is an ambient coordinate system installed when you launch the package, and that system is Cartesian. Now, in the vector calculus package itself, you're constantly changing that background system in order to have properties of the coordinates transferred over to the objects you create. But because of the default coordinate names being understood here in this package, there's very little need to change that ambient coordinate system in the student package. I always just leave it as Cartesian, and I never changed the ambient system, or hardly ever changed the ambient system. And then there's one more thing I want to mention here about spherical coordinates. The default names are r, phi, theta, and that looks mathematical. If to a physicist, that triple would appear as r, theta, phi. And the point I would like to make is it doesn't make any difference what you call these two angles. You can call them u and v, anything you want to call them. It's the position in this triple that determines their role. This second coordinate in that triple is the angle down from the z-axis. And then, what do you call it? Phi, theta, u, v. That position of that letter determines its role. And this third variable is the angle around the z-axis. And that causes all kinds of confusion in Maple too, because this is something unique to the package, not clear across the board everywhere in Maple. The two commands that you might run into to change coordinates, and these are setting the background coordinates, and these are getting the coordinates either from the background or from an object. All right, get and set coordinates. I hardly ever use these two commands. After looking at coordinate systems that the package recognizes. We next look at the kind of vector objects. So here's a table of basic vector objects. There are 4. Free vector, rooted vector, position vector, vector field. Free vector. How would it be entered? It could be entered as a comma b with these wedge brackets around them. Those wedge brackets are just inequality symbols. Or you could use the vector command, and you could put a list, or you could put the wedge brackets. If you include a coordinate system name, then that vector is interpreted as a vector in that system. The default polar variables are r and theta, but if you're working and experimenting and exploring, it's tedious to type out the word theta, or even to use the 4 keystrokes that it takes to get the symbol theta. You might want to just use the letter T. So if you state them in this list, then you have overwritten the default names, and now polar coordinates have the names R and T. Rooted vector. This is a vector that remembers where its tail belongs. That's called the root point. So if you translate a vector in Cartesian coordinates to another point in the plane, that point at which the vector is attached is the root point. And a vector that remembers where its root point is called a rooted vector. Position vector. This is the vector from the origin to the point in the plane. And in Cartesian coordinates, we all understand what that means. So if you create a position vector with this position vector command, it will be a Cartesian vector. This would be a point. If the components are a 1-parameter expression, then this is a curve. If you add the name of a coordinate system, like polar, then these are interpreted as polar variables. In 3 dimensions, F, G, H, this would define a surface. So this position vector allows you to define a curve and a surface, as well as a point. And not only that, there is a companion command that I will mention here. Plot position vector, which will draw a graph of whatever it is that you have defined. If it's a curve, it will draw that curve. If it's a surface, it will draw that surface. And with other options in that command, you can add to the graph of either the curve or the surface graphs of various vectors, whether they're Frenet-Serre vectors, tangent, principal, normal, binomial, derivative fields. So you could graph the acceleration vector. You can define a vector field and have it graph vectors along either the curve or the surface. So the position vector and the plot position vector commands are a pair of very, very useful, very powerful commands in the package. I would say that both these commands, rooted vector and position vector, were not in the original version of this package. They were added when it was realized that there was something lacking in the package the way it was originally built. Then there's the vector field. Use the vector field command, brackets or angle brackets here. These are the mapping from R2 to R2, blah, 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 that puts a vector at every point. And you can define in other coordinate systems. This would be in a Cartesian system. A vector that has a parameter. Suppose you have t and t squared here, or t and t squared here. The package will look at that for many of its uses as a curve, but it is not a vector field. So in order to have the properties of a vector field, you've got to use this vector field command. Now, to make sure that we've covered all of the items that are of interest in about these 4 basic vectors, let's make sure that we've covered all the details. So what happens if you define a free vector this way with angle brackets? If you hit the enter key, you're going to see these e sub x, e sub y vectors, which are the equivalent of I and j in a Cartesian plane, 3 dimensions. If you say polar, then you get r and theta. If you say cylindrical, you get r theta z. If you say spherical, but don't want r, if you are like me, if these 2 letters are in Greek, you want this one in Greek also. So you want rho, then you add the names of the coordinate vectors that you want to use after the word spherical, and then e rho, e phi, e theta. And remember, this is really just a position vector that represents a point. Then the rooted vector, here's a picture that shows you what the rooted vector command does. So there is a plot vector command, which we have listed below under the visualization commands. Plots a rooted vector, root point 1, 2. So this is the point 1, 2. The vector has components -2, 1, so -2, 1. This is the most convenient command in Maple for drawing vectors. There are 2 arrow commands. The original one was in the plot tools command, and they added one to the plots command. They have different syntax from one another, and they're tedious to use. This plot vector command takes a lot of the fussiness out of drawing vectors, because you don't have to say much about its shape and so forth. And it will do a collection of vectors. You can have different kinds, rooted vector, free vector, etc. So that's a useful tool. Position vector. So I've said it's always a Cartesian vector. So suppose you have s squared, s cubed, and you say polar. Well, then this is interpreted as r, see, and that's r cos theta. That's interpreted as theta, r sine theta. So this would be the Cartesian equivalent of something defined in polar coordinates. If you have 3 components, x, y, and f of x, y, then you are getting a surface defined parametrically. This is the surface of a sphere defined parametrically. Radius 1, unit sphere, radius is 1, and then the 2 variables on the surface are phi and theta. And then vector fields. So let's create a couple of vector fields in which you see the E bar basis vectors. And those are the moving basis vectors. But here's the point about these moving basis vectors. They're just symbols. They do not carry the point dependency information that you would expect moving basis vectors to have. Any command that manipulates a vector field has been coded to provide that pointwise dependence of the vector field, of these moving basis vectors. Because of that, if you want to evaluate a vector field at a point, you must use this eval vf, vector field, evaluate vector field command, because that command is what provides the pointwise information for the basis vector. If you just did a substitution into a vector field, you would modify the component, but you would not get the correct modification of the basis vector. And finally, if you use this vector field command to create a vector field, there is an option, output equals plot, and when you get a picture of the arrows of the field. Having created some of these basic vector objects, the next thing you want to know about is the set of commands, or some of the commands that are applicable to these objects. The first one that I always use is this one, basis format. What does it do? That command controls the display of free vectors and vector fields. Default is to show the basis vectors. The alternate is to display these vectors as column vectors. I prefer the alternate. I do not like the default because you have this issue of unbarred and barred basis vectors that took me 2 years of questioning both the program itself and the man who supervised the construction of this package to get straight what the difference between the barred and unbarred basis vectors was. And the secret to understanding that was to realize that points are being represented by a position vector, and a pseudo fictitious position vector is created to represent points in non-Cartesian coordinates. That took me forever to get straight in my head, and it's unfortunate that it's so cloudy. There is an about command spelled with a capital A that will tell you what kind of object and what are its properties. That's useful to know. We've mentioned the eval vf command. The map to basis vector, map to basis command that we have seen already changes coordinates. It will work in a free vector, which will, a free vector is really a point, so it will change the coordinates for a point. For a vector field, it does the job of figuring out what happens to the basis vectors. And there is a convert vector command which will convert between free, rooted, and position vectors. Notice there's no mention of a vector field in here anyplace. Having created these vector objects, differentiation is one of the operations that you can apply to them. So let's see what the basic differentiation commands might be. Diff, that's a top level command, but in the package this command is modified so it maps onto the components of vectors automatically. At top level that won't happen, but it happens here in the package. Also, limit and int, which are also top level commands, map automatically onto the components of vectors. And that property of mapping onto the components of a vector has been inherited finally by diff in the student multivariate calculus package, where students will first differentiate a vector. And so that is available in student multivariate calculus. Don't have to load the vector calculus package in order to get that property. Then there's a gradient operator. Okay, computes the gradient of a scalar, and it will return a vector field. Okay, it does not return a single vector, it returns a vector field. The divergence, del.f, applies to a vector field. Curl, del cross f, applies to a vector field, and it returns a vector field. This one returns scalar. Laplacian, del squared, applied to a scalar, and it returns a scalar. There is a directional diff command, so it computes a directional derivative. There's a directional derivative command in the student calculus package, calculus 1. but there's this command here, and it applies to scalar. There is a useful tangent line command and a useful tangent plane command. Here you get a parametric representation of a tangent line or a line tangent to a curve, and the plane tangent to a surface. It is unfortunate that these two commands don't exist in the Student Calculus package, Calculus 1, because that's where you first run across this stuff. One of the applications of differentiation on vectors would be the Fourier formalism, which is analysis of curves. So let's take a look at what commands are available to do the Fourier analysis. The command curvature, radius of curvature, torsion, tangent vector, principal normal, binormal, T and B frame, they can all be applied to a curve, and that curve can be defined as a free vector with a parameter. So angle bracket t squared would work here, in which goes to show how the origins of this package have evolved. Initially, there was only the free vector and the vector field. So you don't compute the curvature of a vector field, so you needed a way of computing the curvature of a curve, so the curve was represented as the free vector. But there's more machinery in Maple now than there was originally. So curvature, radius of curvature, and notice that one of the options to this radius of curvature command is output equals plot, and then you get a graph of the curve and the circle of curvature. Compute the torsion, tangent vector. Now the tangent vector command, as it stands, simply returns a tangent vector, which is the derivative with respect to the parameter. Takes the option normalized, so now you can get a unit tangent vector. You can have the output be either a plot, which is a graph of the curve and a representative unit tangent vectors, or you can animate the progress or the traverse of a unit tangent vector along the curve. And that same property carries over here to principal normal. You get the option normalized, output equals plot, output equals animation, and same thing with binormal. Okay. Now the T and B frame returns a sequence of the tangent, normal, and binormal vectors, and they are normalized by default. And you can return a graph or an animation. Now that animation is part of what the space curve tutor. So I've just launched a space curve tutor. It lives up here in, I'll show you where it lives. It lives here in Tools, Tutors, VectorCalculus, Space Curves. Alright, so I launched it here from this button for convenience. It has a default curve with a default domain, and this is the default setting, Cartesian 5 T and B frames. So it draws this graph of the curve and crowds it up with 5 T and B frames. I immediately go to plot options, and I use constrained scaling and change to a frame. That cleans up a great deal of the picture. And then I change this to a big number like 30 and animate. So I get one T and B frame traversing the curve. Much easier to understand. And you can tip this thing around, turn it so you can see what the curve looks like if you project it into the xy plane. But that's not the only thing you can get. Let's stop that. That's not the only thing you can get. You can get individual tangent normal, binormal vector animations. You can get an animation of the osculating circles, or the circles of curvature, which live in the osculating plane, the plane formed by the tangent and principal normal vector. You can get a graph of the curvature and a graph of the torsion. So, okay, so you can see that there is the TNB frame command being invoked, and you can use these various options to generate these kinds of figures. So, if you don't want to bother with the commands, you can do it interactively with that tutor. Well, differentiation applied to these various vector objects. How about integration? Okay, so here is a table that lists integration commands in the package. And I will say this before I get started. The physics vectors package has some very nice tools for doing vector calculus. But it has no tools for doing anything with integration. So it will do div grad curl. It will represent vectors very nicely with little hats over the basis vectors and so on. And it does one thing that's done nowhere else in Maple. That is, it will allow you to manipulate vectors for which you did not have to declare components. These are called unprojected vectors in that package, so that it knows the basic vector identities. It's the only place in Maple you can do that. Unfortunately, it has nothing in there on integration, and so you end up having to use two packages. You're teaching two different paradigms. It's just doesn't work. So you're going to have to almost forced to use the Student VectorCalculus package if you're using this in the classroom, because of that lack of integration material in physics vectors. So anyways, here are the commands. Int. Now int is a top level command. It integrates stuff. But it's modified here in the package so that it recognizes some predefined domains. And here is a list of circle, ellipse, parallel to pipette, rectangle. This is the arbitrary region. You defined a region parametrically. Sector applies to circle or ellipse, so piece of either one. Sphere, tetrahedron, triangle. The syntax is different because of these predefined domains. And in the top level, little int evaluates immediately, and capital INT is the inert form of the integral. You don't have that inert form. You do it with an option. Output equals integral. There is a pathInt command, which does a line integral of a scalar along a curve. And it's clearly taken with respect to arc length. And it knows some predefined curves. The arc will define to a circle or an ellipse. A line is a single connector between 2 points. Line segments is a polygonal line. And path is the general curve defined parametrically. There is a line int command. It does the line integral of the tangential component of a vector field. So, although a line integral can be flux, initially it was never taken care of. So It's the tangential component, and flux had to be done separately. Okay, so it knows predefined paths, arc, circle, and circle through these, so you can do a line integral around a circle that's in space, ellipse, line segments, path. You can get a graph of the integration path and arrows of the vector field if you use any of these predefined paths. And notice both the pathInt and lineInt commands can be accessed through the context panel. It's unfortunate that the whole package cannot be accessed through the context panel. But these are two of the handful of items that you can implement through context panel. There is a surfaceInt command which will compute the surface integral of a scalar. It figures out what the element of surface area is. So all you need to tell it is a description of the surface. It knows these predefined surfaces: box, sphere, and then the surfaces you define parametrically. The advantage of this command, the real strength of this command, is that you can have a surface defined parametrically, but it can be defined over one of these known regions. So you can have even think of a plane, but you only want to integrate over that portion of the plane which sits above a circle or an ellipse or a rectangle or a region which you define parametrically, or a piece of a circle or an ellipse or a triangle. And the flux command has the same properties. So if you're in the plane and you have a two-dimensional vector field, it computes the integral of the normal component along curve, and clearly there are some known curves, and you can get a graph like you could get for the line integral if you use these curves, these paths. If you're in space, then you are getting the surface integral of the normal component. So when you do f dot n, you're getting a scalar, and it's going to have the properties of that surfaceInt command. Okay, and again, it will figure out what the appropriate element of surface area is once you tell it what the surface is. And these are clearly are the predefined surfaces that it rectangles, and you can define the surface over a region in plane. And for these options, without defining over one of these restricted domains, you can get a graph that shows you the surface in the field. And there is a set of task templates. So what are task templates? Tools, tasks, browse, table of contents, calculus vector, this is integration, flux, and it's either 2D or 3D, okay, and you have flux through, these are planar curves, and these are surfaces, and for example, this would be for a surface defined over a triangle. This would be a surface defined over a disk. This is a task template. It's inserted by clicking on one of these buttons. Default content means you get all of this verbiage. Minimal content means you get enough to make the thing work. And they were written by me because they are not available through the context menu or panel now. Scalar potential, vector potential, there are commands to compute those, and those are essentially integrations. Now, we've already mentioned some commands that will draw graphs. Here is a complete listing of the commands that provide graphs. We mentioned plot vector. It graphs one or more, either a free vector or a rooted vector. Plot position vector graphs the position vector, and it has options for graphing curves and surfaces and vector fields along those curves and surfaces. You can get a graph of a vector field if you use the vector field command. One of the options is to get the arrows of the field. You can also make use of this vector field tutor, which draws arrows of the field and will draw a curve emanating, flow line emanating from a given point. And you can see down here the change to coordinates, set coordinates. That's because background behind here is the VectorCalculus package. Flowline command, which I'm about to talk about here, being applied to vector field, and that's how vector field and flowline is being drawn. Flowline, it graphs the arrows of a vector field, and one or more, see the command has been modified, that you can give it a list of initial points and you can get flow lines from a collection of points. It's a space curve command. Now if you think about this for a bit, at top level, the plot command can be used to graph a curve defined parametrically. If you have only if you have a planar curve. If you have a space curve, you have to go to the plots package and make use of the space curve command with lowercase letters in the plots package. So this dichotomy has been resolved in this space curve command here in the package. It will draw curve in the plane or in space with the same syntax, the same command name. So a great simplification. It should be, in fact, available at top level, but that's neither here nor there. And then I showed you the space curve tutor, which will do this stuff interactively. The line int command, I mentioned that. It will draw a graph under the right set of inputs. The flux command similarly, and then these commands that we saw for the Frenet array formalism, they draw graphs also with the right options. Having built all this machinery, we should do an example to see how it works together. So here's the calculation of a flux to a surface, three-dimensional, Cartesian. Vector field is here. This is the surface, but it's only that portion of the surface that sits over the disk whose center is at 1, 2 and has radius 1. So I'm going to do a solution with task template. I showed you where they were. There's the path to it. This task template is installed, and initially all of the fields are collapsed, which tends to encourage the insertion of data in an orderly fashion. If you start to randomly stick data here, there, and everywhere, then you have to program the tool to make use of data that's incomplete. That's too hard. So let's pick the coordinate system. It's XYZ Cartesian. Set that system, and now we have to put in the vector field, the components of the vector field. This is x plus y squared. This is x squared minus y, and this is xyz. x, y, z. Then you click continue, and then more fields open up. Okay, so what are the parameters? The parameters are x and y. And x is x, y is y, and z is 10 minus x squared minus y squared. You click continue, and now you have a place to put in information about the disk. So the center is at, I believe it was 1, 2. Yes, so that's 1 here, 2 here. And the radius is 1. And now I have a place to obtain the actual flux integral. And you can see it is a non-trivial integral, and it has been converted automatically by this underlying command to polar coordinates. And then you can ask for its value, and you get its value. And here we can take a look at how you might do this calculation via the set of commands that we have just gone over. So I want to initialize, so I'm going to execute a restart, bring in the student package, and this is that basis format command. If you give it the argument false, it means vector fields will be shown as column vectors. And so here I'm defining the vector field. Then to obtain the flux, I'm going to simply make use of these two versions of the flux command. So here's the vector field. This is how you give it the surface. It's given parametrically, and that's contained in a vector, x, y, f of x and y. And this is how you give the region over which that piece of the surface is defined. These give the coordinates of integration. Surface makes sense to Maple because the vector field carries a coordinate system, and that's where this part is getting its information. But here you have to tell it that the circle is in the xy plane, center, radius, and these are the variables that are to be used in the polar coordinate representation that Maple is going to switch to. When I tell it to output the integral, if I didn't have this r and theta over here, it would use x and y as if x were r and y were theta, and that is extremely confusing. So this is the integral we saw in the task template, and if you don't put output equals integral, then the default behavior of this command is to simply evaluate. Finally, if you wanted to implement that flux integral from first principles, you might do something like this. You would define z of x and y, that's giving you the surface. Define the disk in polar coordinates, 1 plus r cos theta, 2 plus r sine theta. Then you would need the sigma, the element of surface area. Ordinarily there is a dA, which would be either dx dy or dy dx, but Maple does not have a concept of differential when it implements an integral. The differential is in the int command. So although I'm calling this d sigma, it's d sigma short of the differential that should be tagged on. Now I want a normal field on that surface. Since the surface is given explicitly, one way of getting that normal field is to write the vector minus z sub x minus z sub y in 1, or if I write z minus big Z, then I'm defining the surface implicitly, so its gradient would be normal. And so this is a vector field to which the normalize command has been applied. So that's the unit vector field that I need. Then I need to compute f.n, so that's the normal component of the field, times the sigma. But all of that has to be evaluated on the surface. So any letter z that would be in here would have to be replaced with 10 minus x squared minus y squared. So that's what you get here. And then we want to integrate around or over the surface of disk, so we need to change coordinates to those polar variables. So that's what this command does. So now this has been expressed in polar coordinates, and the integral is set with the palette, the calculus palette, double integration template. This is this expression here. It's in polar coordinates, so you need an extra r as the Jacobian, and then d theta dr, 0 to 2 pi, 0 to 1, and this gives you 29 halves pi that we've already seen.